On December 18, 2025, the most sensitive and comprehensive search for extraterrestrial intelligence ever carried out on a confirmed interstellar object reached its conclusion, not with a dramatic discovery, but with a silence that was itself scientifically profound. As the interstellar comet ThreeI Atlas sped past Earth at a distance of roughly 168 million miles, the Green Bank Telescope, a vast 100-meter radio dish located in the radio-quiet mountains of West Virginia, remained fixed on the visitor. It methodically scanned the electromagnetic spectrum, searching for even the faintest indication of artificial technology. The outcome of this high-stakes observation has now placed a firm upper bound on the likelihood of any alien activity associated with the object. If ThreeI Atlas were an active probe, its transmissions would have to be weaker than those produced by an ordinary household light bulb. Such a constraint effectively rules out the presence of any intentional beacon or high-bandwidth communication aimed in our direction. This result represents the culmination of months of speculation and debate, providing a decisive data point in humanity's ongoing effort to distinguish between the natural debris drifting through the galaxy and the possible artifacts of other civilizations. By demonstrating that the object is radio silent down to a transmitter power of just 0.1 watts, scientists have, for this particular visitor, effectively set aside the alien probe hypothesis and redirected attention from science fiction back to the equally compelling domain of fundamental physics. To appreciate the significance of this observation, it is essential to understand the nature of the target itself. ThreeI Atlas was far from an ordinary space rock. It followed a hyperbolic trajectory, entering our solar system from the direction of the galactic north with an extraordinary velocity that peaked above 80 kilometers per second, far too fast to be gravitationally bound to the sun. Discovered in the summer of 2025 by the Atlas Sky Survey, it was quickly recognized as an emissary from another star system, only the third such interstellar object ever documented by astronomers. Compared with its predecessors Oumuamua and 2I Borisov, 3I Atlas occupied a favorable middle ground. It was brighter and passed closer to Earth than Borisov, yet its behavior appeared more stable and predictable than the puzzling Oumuamua. Still, the legacy of that first interstellar visitor weighed heavily on planning efforts. Oumuamua exhibited unexplained acceleration without visible gas jets, a mystery that led some respected scientists to seriously entertain the idea of a light sail or an artificial construct. Although 3I Atlas looked more like a conventional comet from the beginning, the Breakthrough Listen team adopted a stance of deliberate neutrality. The guiding logic was simple. If you do not search, you cannot rule anything out. Even a remote chance that an interstellar object might be a dormant probe or a data collection platform justified a thorough techno-signature search as a matter of scientific rigor. For this task, researchers relied on the Green Bank Telescope, the largest fully steerable radio telescope on Earth. This engineering marvel is capable of detecting radio waves that have traversed billions of years of space. During the observation campaign, the telescope was configured to monitor a broad section of the radio spectrum, spanning frequencies from 1 to 12 gigahertz. This range is especially significant for SETI research, because it includes the so-called terrestrial microwave window, where galactic background noise is minimal, and Earth's atmosphere allows radio waves to pass through with little attenuation. Within this window lies the water hole, a relatively quiet band between the emission lines of hydrogen and hydroxyl, long regarded as a natural focal point for interstellar communication. From a purely physical standpoint, any civilization attempting to communicate across vast cosmic distances would likely choose these frequencies to reduce signal loss. By focusing on this band, the researchers were effectively monitoring a universal calling channel, ensuring that if 3I Atlas were transmitting, the receivers were tuned to the most plausible frequencies. The observational strategy was deliberately conservative and redundant, designed to minimize the risk of false detections that have historically complicated SETI efforts. The team employed a method known as nodding, in which the telescope repeatedly alternates its aim between the target object and a nearby region of empty sky. This on-off pattern serves as a critical filter to distinguish genuine extraterrestrial signals from local interference. In today's technologically saturated environment, the radio spectrum is crowded with emissions from human activity. GPS systems, satellite constellations such as Starlink, high-altitude aircraft, and ground-based radar installations. If a signal appears while the telescope is pointed at the comet but remains present when the dish shifts away, it can be confidently identified as terrestrial interference. A true techno-signature, by contrast, would only emerge when the telescope is locked precisely onto the coordinates of 3I Atlas. Throughout the observation window, the Green Bank Telescope executed these nodding cycles with exceptional precision, amassing terabytes of raw voltage data that captured the rapidly changing radio environment around the object during its closest approach to Earth. Analyzing such an enormous dataset required advanced computational tools, including the Turbo-SETI pipeline, a specialized software system engineered to search for narrowband signals that might betray the presence of artificial technology. Within the turbulent noise of the universe, natural phenomena behave like wideband transmitters. Quasars, pulsars, and diffuse clouds of gas radiate energy across broad swaths of the radio spectrum, producing signals that are spread out rather than concentrated. Intelligence, however, tends toward efficiency. An engineered transmitter would deliberately focus its energy into a very narrow slice of frequencies in order to maximize clarity and transmission range. It was precisely these sharp, concentrated spikes that the SETI algorithm searched for while examining the vast 1 to 12 gigahertz dataset. This task was made far more complex by the Doppler effect. Because ThreeI Atlas was moving relative to Earth at extraordinary speed, any signal it emitted would not remain fixed at a single frequency. Instead, it would gradually shift upward or downward, much like the changing pitch of an ambulance siren as it passes by. To compensate, the analysis software had to account for thousands of possible frequency drift rates, effectively reassembling signals that would otherwise be smeared out and hidden by the object's rapid motion. Overcoming this challenge demanded enormous computational power, ensuring that a drifting artificial transmission would not be mistakenly dismissed as background noise. The level of sensitivity achieved through this approach was unprecedented for interstellar object studies. Researchers determined that the Green Bank telescope was capable of detecting a transmitter with an effective isotropic radiated power of roughly 0.1 watts. To put that into perspective, this is comparable to the output of a typical mobile phone or a low-power handheld walkie-talkie. By contrast, most human deep space missions, including spacecraft such as Voyager and New Horizons, rely on transmitters in the range of 12 to 20 watts to communicate across the immense distances between the outer solar system and Earth. Had ThreeI Atlas been equipped with a communication system even remotely similar to decades-old human technology, it would have appeared as an unmistakably bright feature in the data. The fact that no such signal was found, down to a threshold of just 0.1 watts, implies that if the object were artificial, it would have to be inactive, intentionally radio silent, or using an entirely different method of communication, such as optical lasers or neutrino beams, that lies beyond the radio spectrum altogether. Despite the extraordinary sensitivity of the search, the final outcome was a clear non-detection. The first sweep of the data naturally produced thousands of signal candidates, an expected result given the crowded radio environment surrounding Earth. Through successive layers of filtering, these candidates were steadily eliminated. Signals detected when the telescope was pointed away from the target were rejected. Those that failed to match the precise Doppler drift predicted from ThreeI Atlas's trajectory were removed. The remaining possibilities were then cross-checked against catalogs of known satellites and orbital debris. One after another, each apparent technosignature was traced back to human-made interference. When the analysis was complete, not a single signal could be plausibly linked to the interstellar object itself. ThreeI Atlas was, by every measurable standard, radio silent. Although this result may disappoint those hoping for evidence of first contact, from a scientific perspective, it is exceptionally valuable. A null detection transforms speculation into a tested hypothesis, one that, for this object, can be confidently set aside. This clarity allows researchers to redirect their efforts toward understanding the object's natural characteristics rather than chasing unlikely artificial explanations. The radio silence detected at Green Bank is fully consistent with observations made using other methods, contributing to a coherent, multi-messenger picture of a natural interstellar comet. While radio astronomers search for transmissions, optical and infrared observatories, including the James Webb Space Telescope, examined the object's physical and chemical makeup. These studies revealed cyanogen, diatomic carbon, and water ice, the familiar chemical signatures of ordinary comets found throughout our own solar system. As the object drew closer to the sun, it developed a clearly visible green-tinted coma, accompanied by a faint tail, both classic signs of volatile ices warming and sublimating. The features that had initially sparked speculation, most notably its slight non-gravitational acceleration, were successfully reproduced in models that treated the effect as the result of natural outgassing jets gently pushing against the nucleus, a process long established in cometary physics. When this optical evidence of volatile release is combined with the complete absence of radio emissions, the conclusion becomes difficult to dispute. ThreeI Atlas is best understood as a fragment of ice and rock, expelled from another planetary system long ago, wandering the interstellar void until chance briefly brought it into humanity's view. The importance of this study extends well beyond identifying the true nature of ThreeI Atlas itself. It highlights how far planetary defense and SETI capabilities have advanced. The ability to move from the discovery of a fast-moving interstellar object to a focused, ultra-sensitive radio search in only a few months represents a major logistical achievement. In earlier eras, telescope schedules were often fixed years in advance, leaving little room to respond to fleeting targets of opportunity, such as interstellar visitors. The ThreeI Atlas campaign instead showcased a new level of scientific agility, driven by rapid coordination between optical survey teams and radio observatories. This readiness matters, because the next interstellar object could appear at any time. Statistical studies indicate that thousands of interstellar objects may be passing within Neptune's orbit at any given moment. As sky surveys become more powerful and comprehensive, discoveries of such objects will only increase. The procedures refined during the ThreeI Atlas observations, choices of observing frequencies, nodding techniques, and Doppler correction algorithms, now form a tested blueprint for future searches. In a sense, the scientific community is practicing for the moment when a genuine signal might finally arrive. At the same time, the natural explanation for ThreeI Atlas offers a different, but no less compelling, form of cosmic connection. Its close resemblance to comets from our own solar system suggests that the processes shaping planetary systems operate in much the same way throughout the galaxy. The fact that a star system many light years away produced an object containing the same basic water, carbon, and nitrogen chemistry that contributed to Earth's formation implies that the raw ingredients for life are widespread, not rare. ThreeI Atlas can be thought of as a free sample from a distant world, delivered directly to our cosmic doorstep. By analyzing its isotopic ratios and chemical composition, scientists are effectively conducting an exoplanetary geology experiment without ever leaving Earth orbit. The absence of radio signals simply tells us that this package arrived without instructions or a sender's note, leaving chemistry and physics as the only means to trace its origins. As ThreeI Atlas continues on its outbound path, passing near Jupiter's orbit in March 2026 before eventually leaving the solar system for good, it leaves behind a rich archive of data that will be studied for years to come. The non-detection across the 1 to 12 gigahertz range helps constrain elements of the Drake equation, particularly those related to the abundance of active technological probes. It suggests that if advanced civilizations exist or even spread through the galaxy, they are not advertising their presence through loud, omnidirectional radio broadcasts. This realization may push future searches in new directions, such as optical SETI efforts aimed at detecting laser flashes or artifact-based searches for waste heat from megastructures like Dyson spheres, rather than traditional communication signals. The silence of ThreeI Atlas thus becomes a valuable measurement rather than an empty result. It narrows the search space and prevents future researchers from repeatedly exploring the same unproductive frequency bands. In the end, the breakthrough listen observations of ThreeI Atlas stand as a clear example of human curiosity guided by the scientific method. When confronted with an unfamiliar visitor from deep space, humanity did not rely on fear or unfounded speculation. Instead, we pointed our most advanced instruments toward the sky and sought a direct, empirical answer. There is something deeply unsettling about an object that refuses to behave according to the rules the universe is supposed to follow. Most astronomical oddities eventually settle into familiar categories, reduced to catalog numbers and routine explanations. ThreeI Atlas has done the opposite. With every new observation, it has become harder to explain, more resistant to classification, and increasingly disruptive to the assumptions astronomers use to understand interstellar visitors. What began as a faint, distant object drifting through our solar system has evolved into one of the most controversial astronomical subjects in recent years, not because of what it is claimed to be, but because of what it clearly cannot be. From the moment detailed data became available, ThreeI Atlas began violating expectations. Its most remarkable feature is not its path or brightness, but a structure that should not exist if the object were a natural comet. News coverage initially framed it simply as a comet entering the solar system and developing a tail, but that simple description quickly unraveled. Public discussion escalated when Avi Loeb suggested there could be a significant chance the object was technological in origin. When pressed on what that meant, he compared the situation to a blind date on an interstellar scale, emphasizing that the universe is often more imaginative than humans and that observation must come before judgment. Instead of displaying a typical comet tail flowing away from the sun under the influence of radiation pressure and the solar wind, ThreeI Atlas exhibits a massive, coherent anti-tail that points directly toward the sun. Observations reveal more than 7 tightly collimated jets emerging from the object. From the outset, researchers considered 2 possibilities: that these jets were naturally produced by volatile ices sublimating from the surface, or that they could represent controlled emissions, similar to thrusters on a technological craft. This anti-tail is anything but subtle. It dominates the object's appearance, extending hundreds of thousands of kilometers sunward and overwhelming any faint trailing features behind it. In cometary science, anti-tails are usually rare optical effects caused by viewing geometry and dust alignment. What is seen here does not fit that explanation. The structure is persistent, well-organized, and physically oriented against the strongest force acting on small bodies near the sun. High-resolution images from the Hubble Space Telescope added another layer of difficulty. When processed with advanced rotational gradient techniques, the inner region of ThreeI Atlas revealed not 1 or 2 jets, but 3. These jets are arranged with striking regularity, spaced roughly 120 degrees apart in a symmetrical pattern that appears almost engineered. One jet aligns closely with the sun and forms the core of the antitail, while the other two extend sideways, maintaining nearly constant angular separation over time, even as the object rotates. Symmetry of this precision is not impossible in nature, but in chaotic systems like cometary outgassing, it is exceedingly rare. The object is rotating with an estimated period of about 16 hours. In a typical comet, rotation causes jets to smear, wobble, and lose coherence as they extend outward. In contrast, the sunward jet of ThreeI remains astonishingly narrow and stable. It stretches outward like a rigid beam, more than 10 times longer than it is wide, implying that its alignment with the rotation axis is accurate to within just a few degrees. For this to occur naturally, the rotation axis would need to be almost perfectly aligned with the direction of the sun. Statistically, such an alignment is highly unlikely to happen by chance, yet it appears to be exactly what is observed. At first, conventional comet models were pushed to their limits in an attempt to account for these features. One proposal suggested that sublimation of volatile ices, especially carbon dioxide, could drive unusually powerful jets. Near the sun, frozen CO2 can sublimate violently, producing stronger outflows than water ice would at greater distances. In principle, this could explain elevated activity. However, this explanation quickly runs into fundamental physical constraints. Gas produced by sublimation has a maximum velocity set by thermal physics. For carbon dioxide, this speed is only a few hundred meters per second. While that seems fast on human scales, it is extremely slow compared to the solar wind, which travels at hundreds of kilometers per second. This enormous difference creates a critical problem. Gas expelled sunward from a comet cannot move unimpeded. Almost immediately, it encounters the solar wind, a continuous stream of charged particles flowing outward from the sun. The ram pressure of this wind overwhelms slow-moving gas, forcing it back and sweeping it into a trailing tail. Detailed calculations show that under realistic conditions, gas from natural sublimation cannot remain collimated in a sunward direction beyond a few thousand kilometers. At most, around 5,000 kilometers from the nucleus, the solar wind should stop and reverse the flow. This limit is not a matter of interpretation or modeling preference. It follows directly from conservation laws and measured properties of the solar wind. If ThreeI were a normal comet, its antitail could not sustain streaming gas beyond this distance. Beyond that point, only dust particles, largely unaffected by electromagnetic forces, could continue moving sunward. Gas, especially carbon dioxide, should be swept away. This is where observations from the James Webb Space Telescope fundamentally altered the discussion. Spectroscopic data from Webb did not merely detect dust or reflected sunlight. They revealed molecular signatures of carbon dioxide far beyond the expected cutoff distance. CO2 was detected tens of thousands of kilometers from the nucleus, with evidence suggesting it extends to distances greater than 100,000 kilometers. This single observation pushes the behavior of ThreeI beyond the boundaries of established cometary physics and leaves the object standing uncomfortably outside any familiar category. This is not leftover gas lingering near the nucleus or a brief outburst frozen in time. What is observed is a sustained, elongated column of gas aimed directly at the sun. Once this evidence is taken seriously, the conclusion becomes unavoidable. Natural sublimation cannot account for what is being seen. There is no physical process by which carbon dioxide gas expelled at a few hundred meters per second could push against a solar wind moving thousands of times faster and still remain organized over such enormous distances. The mathematics does not accommodate it, and the physics offers no loopholes. If gas truly exists within the antitail on these scales, it must be expelled at velocities far beyond anything a natural cometary process can generate. This realization represents a decisive shift. Sublimation-driven activity is the defining trait of a comet. Remove that mechanism, and the object no longer qualifies as a comet in any meaningful way. Whatever ThreeI may be, it lies outside the physical limits of known cometary behavior. At this point, the discussion is no longer about differing interpretations of data, but about classification itself. The object violates the very criteria that justify its label. When established models fail, speculation inevitably follows. One idea that has been raised is propulsion. Modern ion engines already used on human spacecraft eject ions at speeds ranging from several kilometers per second to tens of kilometers per second. At such velocities, expelled material could plausibly travel tens or even hundreds of thousands of kilometers before being overwhelmed by the solar wind. Notably, recent research into advanced propulsion systems has explored alternative propellants, including mixtures that involve carbon dioxide. Although xenon remains the most commonly used ion engine propellant due to its favorable mass and ionization characteristics, carbon-based molecules are actively being studied as potential supplements or replacements. Another possibility does not involve propulsion at all, but shielding. Plasma physics provides well-established mechanisms by which charged particles can deflect other charged particles. The solar wind is composed mainly of ions and electrons, precisely the kinds of particles that respond strongly to electromagnetic fields. In principle, a dense stream of ionized gas could act as a barrier, absorbing or deflecting incoming solar wind particles before they ever reach the nucleus. Plasma shields are not speculative fantasy. They are actively researched concepts for protecting spacecraft from radiation and micrometeoroid impacts. The engineering challenges associated with such mechanisms are enormous, but the underlying physics is well understood. The sheer scale of the anti-tail linked to ThreeI Atlas makes this idea particularly intriguing, extending hundreds of thousands and possibly even close to 1 million kilometers. Such a structure would intercept a substantial fraction of the solar wind. Whether intentional or simply a byproduct of some other process, it would offer significant protection to whatever lies behind it. While this interpretation remains speculative, it aligns with the observations far better than sublimation ever did. Even more speculative ideas have been proposed, including the suggestion that what appears to be dust within the anti-tail may not be dust in the conventional sense. At microscopic scales, particles can interact with electromagnetic fields, absorb energy, and be transported by solar forces in ways that differ markedly from ordinary dust grains. If such particles existed, they could potentially extract energy from the solar wind and transfer it back to the nucleus through electromagnetic interactions. There is no direct evidence for this scenario, but the idea highlights an important reality. Once natural explanations collapse, the range of possibilities expands dramatically. It is crucial to be clear about what this argument does and does not claim. It does not assert that ThreeI Atlas is artificial, nor does it present evidence of extraterrestrial technology. Its conclusion is far more limited and far more important from a scientific perspective. It shows that the object cannot be explained as a comet. That conclusion stands regardless of what explanation eventually replaces it. Whether ThreeI Atlas turns out to be a previously unknown class of interstellar object, a fragment of some exotic astrophysical process, or something entirely unforeseen, the comet designation no longer fits. Science advances not by clinging to familiar categories, but by discarding them when the evidence demands it. ThreeI Atlas has forced exactly such a moment. The combination of geometric symmetry, extreme structural stability, physically impossible gas dynamics, and direct spectroscopic detection of carbon dioxide far beyond theoretical limits forms a consistent, testable case. It does not rest on a single anomaly, but on multiple independent lines of evidence that all point to the same conclusion. Future observations may clarify the nature of this object, or they may deepen the mystery even further. Expanded spectroscopic studies could reveal whether additional molecules are present in the anti-tail, whether ionization states vary with distance, or whether entirely new anomalies emerge as ThreeI Atlas continues its departure from the solar system. What is already evident, however, is that this object has exposed weaknesses in long-held assumptions about interstellar visitors. For decades, astronomers have expected such objects to resemble familiar bodies from our own solar system, shaped by similar processes and governed by comparable behaviors. ThreeI Atlas challenges that expectation. It suggests that the population of objects traveling between stars may be far more diverse than previously imagined. In doing so, it serves as a reminder that the universe does not owe us familiarity, and that sometimes the most important discovery is recognizing that an old explanation no longer works. At this stage, the question is no longer whether ThreeI Atlas is a comet. The evidence indicates it is not. The real question is what it is, and whether we are prepared to recognize something genuinely new when it passes quietly through our cosmic neighborhood.